是把我们移到那个有一个那个就是那个应该是个 panel 吧？对对对对对对对，要不然就没办法，两个都得。对对，但是我可以专业上经营就行好。
Record progress.
你把那个声音关。你看用哪个？Yeah. We can probably still wait for another 5 minutes. Yeah.
Yeah. Yeah, I took over from the year. Is kind of move on back. Ah. No, but I'm pushing over. No, I'm speaking over.
Okay, probably I guess we can start. Yeah, so thanks for everyone to join today's SSC seminar. So Hui is not here, so I'm on her behalf to host the seminar. So today we are honored to have Dr. Wei Bao from University to give us a talk on efficient distributed machine learning, joint algorithm, and systems approach to our department. And before the talk, I'm going to give a brief introduction on Dr. Bao. So Dr. Bao received a PhD degree in electrical and computer engineering from the University of Toronto in 2016. He is currently a senior lecturer at the School of Computer Science at the University of Sydney. So his research focused on networking, edge computing, and distributed machine learning. He received the Best Paper Award in ACM International Conference on Modeling, Analysis, and Simulation of Wireless and Mobile Systems in 2013 and 2019, and the IEEE International Symposium on Network Computing and Applications in 2016. So he is also the co-CIs for 2 ARC discovery projects and currently leading one of linkage project. So without further introduction, let's welcome Dr. Wei to give us a talk.
Thank you very much, Dr. Yuan. Today I'm going to introduce our recent research progress about this distributed machine learning. So I'm also here to looking for some potential research collaboration opportunities. So at the very beginning, I need to give you a very quick introduction of the background. So we all know this AI and machine learning became this double-edged sword. So of course they have reshaped many industries and our lives. But in the meanwhile, there is a significant cost, especially in hardware and this energy consumption. For example, training this ChatGPT is very energy consuming. And what is more interesting is that people are talking about this energy in the data center, but what actually happens is that in this in the edge, because there are so many computers and so many like edge devices like your cell phones. So in that case, and the energy cost there is even more. So in that case, and we need to find some way to improve this efficiency of this AI and machine learning these applications in both this data center and at the edge. So basically, I'm going to introduce our solution. So we have this 2 dimensions, and one is this model training or inference. So training means that we train the model, let the model learn, and the inference means we ask the model to make predictions. And also in another dimension, and we have this algorithm-based or system-based. So algorithm means we directly improve the algorithm itself, but system means that we want to feed the algorithm to the system so that by saying, for example, like resource allocation so that they can improve this efficiency. So we have 2 dimensions, and so we put them in this, so we have 4 quadrants. So we have some solutions in this domain, this 2-dimensional domain. So firstly, we have this federated learning. So this is more in this training side. And also we have this efficient inference, which is in the inference side. And also video application is like one of the most important applications and in many AI applications. So we also have some works there. So this is in the system side, and also we are going to talk about this controllable processing time, which covers all these quadrants. So now let's look at our first like research topic about this federated learning. So federated learning is very popular these days. So because people want to train the model without sharing their original data. So in that case, and they just transmit their model instead of transmit their like original sensitive data. But there could be some problems like this data are non-ID, so meaning this non-independent and identically distributed. And also we have this heterogeneous devices, so it will cause this slow convergence and high energy consumption. So the solution is that we have this in the algorithm side, we have this momentum for acceleration, and also in the system side, and we can have the 3 tier, so which is a better system. So before talking about our own solution, we need to have a quick review of this federated learning itself. So this is a standard called this Fed average. So we have 1 server or 1 aggregator and n workers or n clients. And each worker has its own data size di, and then like with the loss function fw. So which is a weighted sum of this local loss function. And we want to minimize this this fw. So this is the training process. So the Fed average, so in each iteration, and each client will do its own this gradient descent. And for every tau iterations, and they will aggregate at the server, and the server will redistribute it. So this will continue so that the model will be jointly trained. So we see that this Fed average may not have this good convergence performance. So what we have done is like, firstly, we have this momentum to improve this convergence. So what is a momentum? So basically this concept is borrowed from this physics. So basically we want to increase the dimensions where gradients point in the same direction, and we want to reduce the dimensions where the gradients are changing directions. So basically if like we have this gradients is fluctuating and moving to right, so the right is the good direction, and the up and down is bad direction. So we want to let it going to right, not fluctuating. So we use one type of this momentum called this natural accelerated gradient. So this we have this momentum term m, and so this will be added to this traditional gradient method. So the momentum is the weighted sum of this previous momentum and the current gradient, but the current gradient is made at this point, which is a prediction. And also this the model itself, W, will be updated from the previous one by adding this the momentum. So by this way, we use it in this federated learning. So for each worker, it will generate its like model update as well as this momentum update, and every all iterations, and the workers will need to upload this model and as well as the momentum to this aggregator, and the aggregator will aggregate both this model and the momentum. And so in another algorithm called this fast slow momentum, and this aggregator also has this one hidden momentum, which is just a private momentum by this the aggregator, but this is not going to share with the clients. And then like this will conduct this model update, and will distribute the model and this momentum to the workers. So in this case, and we can prove that the conversion rate is 1/t, so meaning that the output at the tth iteration, we evaluate this gap from this the optimal. So this is bounded in this way, And also we have shown that it's a fast slow momentum. So this is double momentum is better than this single momentum, which is better than this no momentum. So we also want to evaluate especially in this NIID case. So how do we evaluate the NIID? So we have 10 classes of data with 10 labels, but we say that each user or each worker only has 3 classes, right? So in that case, and the distribution of the data is pretty biased. So in that case, we can evaluate the performance of the 3-class situation or the 6-class situation. So in this case, and we can show that the performance is better. So from this algorithm side, and we have this momentum one, but in the system, we also want to improve it. So what we can do is that we can change from 2 tiers to 3 tiers. So we can see like in the 2-tier case, and everyone is directly talking to the cloud. So in that case, and we can see all these communication links through this public internet. But we also we can also add this the edge here in the middle. So in that case, the communication will be constrained in the local networks. And then like we can see the communication through this very expensive public this link. The number comes from 6 to 2. So this is will save this communication cost. But now we have 3 tiers. So we need to change it a little bit. So we have the 2 levels of this aggregation. So every tau iterations, and we need to have the edge aggregation, and every tau pi iterations, we need to have this cloud aggregation. So what we can do is that we have this like 3-tier this algorithm. So still every iteration, the worker will do the momentum and the model update. Every tau iterations, and there will be this edge tier aggregation, so that the edge tier will aggregate this momentum and this model. In the meanwhile, this is still the edge tier will need to calculate its own private this momentum, and every tau pi iterations, and there will be aggregation and redistribution in the cloud tier. So basically we can see that so every tau iterations, and there will be this aggregation. Every tau pi we have iterations, we have this one. But we also found like a very interesting thing is because we have 2 momentum in the 3-tier system. So these 2 momentum may disagree with each other. They may cancel with each other. So in that case, and we need to find another way so that we have this adaptive factor. So if they disagree with each other, and we need to reduce their bad effect to the algorithm. So still the conversion rate is 1/t, and we have shown that the performance better than this 3-tier without momentum. So this here we also want to show that so the duration to train the model using this both the momentum and 3-tier is much better. So compared with these other algorithms, like we want to show, like if we want to reach this a predefined accuracy, for example, 95, and how long it will take. So we can see that so this is so this 3-tier with momentum will perform much better than these other algorithms. So also this is only like one example of like what we have done in federated learning, but like we have also done several other things and related to federated learning, like this communication and computation trade-off, and other methods for acceleration and semi-supervised federated learning and anomaly detection. So this is our work in this learning part. And next, I'm going to introduce our like ideas and in this inference part. So for this inference, what can we do? So one issue is we have this edge device, and which is very limited with computing capability. So in many situations, I don't have this enough this time to process the large model. So what we can do is that we have this early exit. So we exit the model earlier with a lower accuracy. So basically, this is a trade-off between the time and this quality, right? So in this case, and we have this model with early exits, and so we can select which place we can exit. So in that case, and we have like different processing levels or processing delays, and with different levels corresponding to different delays and different accuracy. So in that case, and we need to determine like which exit point or which level we need to process. So we consider this application, which is like we have this sequence of tasks. So with a fixed inter-arrival time. So this we can see that this fixed inter-arrival time means that this is a constant, though this is a video application, right? The frames are arriving with a constant inter-arrival time, and also we need to complete this processing before the deadline. So deadline, there is a fixed offset from the arrival time to the deadline. So it's still this video processing because we process each frame and need to be played out at the player. So in this case, and for each task, we want to choose which level we want to use. So obviously we can use the smallest level, but we can see, so the system is idling here, so it's not fully utilized. Or we can use the oldest highest level, but we don't have enough time, so they will miss the deadline. So we need to have this different selections for different frames or this job. So what we can do, so we want to have this optimization problem. So we want to maximize the overall this accuracy. But this is like NP hard, so this is converted to this subset sum. But we can have this pseudo polynomial time solution when we assume this time is slotted. So we first find that this if the job arrives earlier, and they must be processed earlier. And then like we can use dynamic programming and solving it with this find this optimal solution, but with the complexity this one. So we can see this complex. So TC is the time horizon. So time horizon means like what is the starting point to this the end of the system. So basically this is a TC. So basically this is so because like this time is so slotted. So basically you can see this indeed that is pseudo polynomial, and but in reality, so this is acceptable because like if TC is not that large enough and the granularity is not that small, and then like this is acceptable. For example, we have like 10 seconds or like even one minute, and like the time granularity is 100 milliseconds, so that looks okay. So we have this experiment. So this scenario is that so usually we can have this cell phone connecting to the cloud, and so we usually offload this computing task to the cloud. But suddenly when we enter the tunnel and the connection is down, and we don't have the connection, everything we have is the device itself. So we need to depend on the device. So in this case, and we can we use this early exit. So we tried in this the tunnels in Sydney. So basically we enter the tunnel, and then like the signal is down, and we use this algorithm. But still, like we tested this our algorithm with some other algorithms, and we can show that is indeed is performs better. So we also have like other relevant work in this inference, and the first one is just like this DNN model partition. So one part is in the device, and the other part is in the cloud. And also we have like other like early exit decisions, which is more dynamic. So in this example, we as long as we determine which exit point, and we need to stick to this decision, but we can have a more dynamic one. So say like just before exit point 1, and we decide whether go out or continue, and then like at beginning of exit point 2, and we determine whether to exit or continue. So basically we have more decisions. So when we meet each exit point, we have we can make the decision. So that is even more dynamic. So the next part is about this efficient this video processing. So because this we have a lot of like this video applications. So this is it's a very important one. So we have this our solutions in this part. So basically what we have done is this edge assisted this video super resolution, or this VSR. So basically because during the COVID, right, so everyone is using like Zoom, right? So this is very important. So people want to have this high resolution, this video at the end, but sometimes and the performance is low because like we have the limited network bandwidth, or like this the 4G is not very good, and right. So in that case, and the traditional approach is just to improve the bandwidth, but this is not the best one. So we want to build this our solution that we use just like the current system without like an investment on the hardware. But we at the receiver, and we use this deep neural network so that they can recover the video from low resolution to high resolution. And also like this DN model, because like there are existing this DN models and in this super resolution, so we don't want to rebuild everything from the scratch. But one difference is that so here this Zoom is on live video, real-time video, right? So but this existing ones usually for this stored video, we need to change it a little bit. So this just a design outline, just like we have the camera, which could be very weak, and it will transmit the video, like low quality video in the low bandwidth network, and the receiver has the video received, and will use the DN model to super resolve it. And so the DN model design is pretty straightforward, and we just use like borrow like existing ones, like this alignment module, propagation module, like upsampling module, and so we don't need to build them from scratch. But what we do need to revise is this the one-way propagation of the information, because like because you want to super resolve the current frame, and you only have the past information, you don't have the future information. So it's a one directional propagation, right? So but in the traditional this video super resolution, right? So you have the current frame, and you have this the previous frame and next frame in the stored video. So in that case, you have bi-directional information. So you need to change this a little bit, so that so you need to use this the connection of these different parts will become this single direction. So we have this system, and we test it in this our lab. So we use this like a cell phone to have to record the video as an online video, and then like we have this we use just like our like server and to super resolve it, and so we can directly view it, and we can see here. So basically, but I think this is through the Zoom, so it's not that clear not as clear as what I have here. So basically, we can see that here, like these numbers can be seen after this super resolution, but these numbers here cannot be recognized. So we also have some other relevant work. So first one is this joint super resolution and this bit rate adaptation. So this is very interesting because when you are watching, say, like YouTube, right? So you will experience this fluctuating resolution when the network is fluctuating. So when the network bandwidth is low and the resolution is also low. But now we have this if we consider super resolution here, we have like two things. One is this transmitted resolution, the other is this super resolved resolution, right? So depending on this bandwidth and the computing resource, say like you transmit at 600 and 360p, and you super resolve to 720p, right? Or like you transmit directly at 720p, right? So basically you have like two solutions, and like when you want to do the transmission. And also like we have this the joint video denoising and the super resolution. So because like during the night the noise is pretty the large, and due to so you can see like when you have the video during the night the noise is large, and we need to have this joint denoising and super resolution. The reason is like if there's a noise and you directly super resolve it, and the noise will become propagated a lot. So you need to consider this too. And so in the end, and we want to introduce our like this controllable processing time. So this is very important for when we allocate these jobs for this AI and machine learning tasks. So we have these multi-users and the multiple servers, and the servers or the machines will need to process the tasks. But as I mentioned, like we have like a limited resource. So in that case, we can't process everyone 100%. So we have this controllable processing time, like in the inference, and we have this different models, small model and large model, right? So they have different quality. And in the training, right, it's also like a very obvious, like how many iterations we want to train, right? So if like we train like a smaller number of iterations, and then the quality will be lower. But we have this unknown future. So that means like so when you have the task arriving and which level you want to allocate. So if you do it in the highest level, so there's no room for like another like a high value task. Or if like you use the lowest level, and so you just give it out, and but there's no task arriving, so you have like you don't have anything to do. So in order to address this one, so we have this online algorithm so that we can make these decisions for this unknown future. So here we consider this one as a graph. So we have this U and V. So this U means the machines, and V means the tasks possibly arriving. And so they are in this bipartite graph because like one task can only be done by like a subset of the machines. For example, this task can only be done by this machine. This task can be done by this machine or this machine. So we also have this set of levels. So in that case, corresponding to different delay and different quality. So the distribution to processing follows this known distribution. So once this the task arrives, and we can allocate this level and the machine to the task, and so the machine can either accept with a probability, or like it can reject. So that when it rejects, and it will cost the penalty, and so there's like a penalty budget. But if each time it rejects, it will the budget will be reduced. So when there's no budget at all, then the machine cannot work anymore. So So basically, this the budget is like delta U, but we also allow this delta U to be infinity, meaning that they can reject any number of times. So for here we assume this online setting because we know this is the future is not known. What we know is this the probability that task U arrives with probability PVT at time t. So this probability is known, but whether it arrives, we only know this event at that day. So for example, like I know the probability distribution of the weather tomorrow, but the weather that is sunny or not, I only know it's tomorrow, right? So this is a assumption called this non-adversarial distribution. So in that case, and when the task arrives, and we need to decide which machine and the level to process. So we can see there are some like unknown like feature in this problem, right? So what we can do, so we need to design this online algorithm, but what we can do is like we design this offline benchmark, and we use the solution to this offline algorithm, and so that one is a parameter to be used to guide this online algorithm. So what happens is like we have this offline optimization problem as a benchmark, and so this is offline linear programming. So we have the variables U, V, L, T. So the physical meaning of this is that we assign this machine U level L to this task V at T with this probability. So in this case, and we have this maximization of this expected overall reward, and under some this constraint following the intuition. So in that case, and we can solve this problem with the solution X star. So this value, of course, like this one cannot be reached in reality because like here, because we don't know the future, right? So in that case, this is just this ideal case is upper bound. But what we can do is like given this X, and we can use it to guide the decision. So in the online algorithm itself, when the task arrives at T, and we choose this UL with what probability? With this probability. So this is calculated from the X star value. So basically from this offline setting, we find this X star, but we use it to guide this online algorithm. And then like, but sometimes on this the machine U doesn't have this budget, or like so it's occupied. So in that case, we can't allocate to it, and so in that case we need to discard the task. So how can we analyze the performance? So for online algorithm, we use something called this competitive ratio. So competitive ratio means that the expected reward of your algorithm is larger than or equal to alpha times of this expected of this optimal one. Okay, so given this optimal one means that you know the future, you know the everything in the end, right? So you have the optimal solution. So if alpha equals to 1, so that algorithm is optimal, right? But this is always not possible, right? So we want to find this competitive ratio, and the competitive ratio should be as large as possible. So what we can prove is that the algorithm is half competitive for this unlimited rejection case, and is about 1/3 for this limited rejection case. So of course we have this do some like a trace-driven simulation, and we show that the performance is looks fine for our this algorithm. So in that case, we have introduced like what we have done, but I also want to talk about what we are thinking we can do in the future. So still like in this this 4 topics, and we consider for this federated learning. So for federated learning, because like now for federated learning models themselves, and usually because they are trained distributedly in a distributed fashion. So So the model itself could be small. So in that case, and the cheap model is trained, but like we may use like expensive model in the server to help it by using this distillation. And also we consider like because nowadays and we don't always have this the true data label. So in that case, we consider this weakly supervised federated learning. So in this distillation, and we can see that the small models are trained, but at the aggregator, there could be a large model, which is called a representative model. So this can use to help train this model. So in that case, it will help it to get better performance. For this inference side, so what we have done is this the early exit, and so basically this one is not ideal because like it doesn't consider the content itself. So in reality, for example, here and when the situation is very simple, right, we can use a very small model, so it's enough. But when the situation is more complicated, right, so we need to use a more complicated model so that the accuracy will be large, will be high enough. So in that case, and we need to consider this content aware this approach. So if the content is simple and we don't need to use too much energy, if the content is like more complicated, we need to adapt to this to different models. For this video processing, so this one is also very interesting. So here, what we can consider is like we have basically why do we need this video? So basically, we have like two like general categories of these applications, right? One is for human, the other is for machine. So human is like you just want to watch the video. So in that case, we want to have the video enhancement. But for the machine, right, you want to like calculate how many cars in this minute, right? So it's a video analytics. So that's just for machine. So basically for human, for machine, we need to have different ways to process them. So for human, we want to have this enhancement, but based on the human experience. For example, you are watching the football game and there is a goal and you want to it in very high resolution, right? But when there's advertisements and you just don't care. So basically it's a kind of this depending on the human's experience. But for machines, say like video analytics, right? So sometimes even in very low resolution, it doesn't matter, the machine can still recognize it. In this example, say, so we have this scenario and so in this frame and here, there's nothing. And here there are a lot of like cars. So in that case, and we just transmit those three patches in low resolution, but this patch in high resolution, right? So if you do this for human, that is really bad, right? So you have very distorted this frame. But that if you want to do them for the machine, so this is totally fine. And for this controllable processing time, yeah, so basically we still in the previous example, and we don't consider this peak hour or this off-peak hour. So we can't delay the job. So basically what we can do is like if the job is not very important, and we can delay it until this off-peak hours, and we can also lower the processing level during the peak hour, and by matching the supply and the demand of the electricity, for example. For example, here we have this renewable energy. So when there's enough renewable energy, and we can process in higher level. But if there's no, and we either delay it or we wait for future. Okay, so in the end, I just want to make a summary. So basically, we consider this how to improve this efficiency in 2 dimensions, and is the training, inference, and this algorithm system dimensions. So for federated learning, and what we have done is the momentum and 3 tiers to improve this convergence. But in future, we want to do this distilled or this compressed model for federated learning. And for inference, and we introduce this early exit. And in the future, we want to do this content aware, this selection or early exit. And in the part of this video processing, and we have done this real-time video resolution. But in the future, and it's very interesting to do this real-time video enhancement and analytics using different approaches. And for the controllable processing time, and we have this online algorithm with competitive analysis. But in the future, and we also consider this like the matching the supply and the demand. Okay, I think that's all for my presentation. Thank you very much. So I'm happy to take any question.
Okay, so probably we go the offline question first, then we go to online session. So any questions here from the audience? Okay.
When you had that slide with like the frame schedule, does that mean like you can essentially like tune it so that it uses like the perfect amount per device? Like you can kind of use the whole computer, you know, if it's a crappy one or a really good one, like. Yeah.
Okay, so so basically, if so in this situation, right? So if you use the lowest levels and so you can like catch the deadline, but the performance, the accuracy is very low.
Okay.
Right? But if you do this one, and the accuracy for this frame could be high enough, but you don't have enough time to process the next one.
Okay.
And because you sometimes you use high level, sometimes you low level. Yeah.
How does the accuracy drop off? Like, is it?
The drop loss depending on these different applications, right? So
Okay.
yeah, so it's depending on different model. So what we can do is like we train the model and we have different exits and exit points, and we test it in different situations, and so we know this average, this accuracy. So we use it as the input of this algorithm. Yeah. So they call this profiling. Yeah.
Thank you so much. It was very interesting talk. So why do you call this early exit?
The early exit is because like we can have this exit at early stages. Yeah.
In the
at different point. This AlexNet is not that obvious, but here we can, this ResNet is more obvious. We can exit at 2, right, and 37 and all at the end, right?
Okay, I got it. So have you ever tried to have different models that, for example, are preloaded in the memory and then you can select,
so basically this is just like equivalent to this model selection. But for model selection, you need to deploy different models in the same machine, right? So basically it's in the memory, so it's larger. But for exits, so you just deploy one model. Yeah, so that is more convenient. Yeah.
In terms of implementation in these kinds of early exit, what you are doing in the, for example, deep neural network, is it easy to implement or?
So for this one is I think this one is easy to implement. Yeah, just tell it which level you want to exit, and then like just like the input argument, and then that is done.
Thank you so much. It was very interesting.
Yeah, I have a follow-up question on this early exit. So just wondering, because we know right now we also have the on-device models, right? So they're already very compressed and compact. So just wondering, any like companies or apps adopt this early exit, or this is just the topics focused on by the academia?
I think like in the previous years there are some like examples, but not because like they just put everything all together. Yeah, they have model selection is good enough. Yeah, but basically they have the same meaning, right? So like they don't need to use just one model. They have this multiple models. Yeah. So multiple models are there in real systems. Yeah.
Okay. So okay, good.
Yeah, I have a question is about your first momentum in federated learning. It seems like you're trying to direct the learning directions. Is that similar to kind of you are doing, because there's many work doing some kind of adaptive learning, right? To federated learning, is that similar? Or do you think which one is better? And whether in your approach, when you're moving like that, does it trade off by the accuracy?
So you say like adaptive learning. So what is
Adaptive learning, right?
okay? So what exactly is that? So
Because the learning right sometimes at the clients, they could be adaptively changed.
oh yeah.
Yeah. So those approach, many papers also focus on that area. So is that similar to, I think that looks similar to your work, but I'm not too sure whether which one has the better performance for the convergence.
Because like this is just focusing on this specific this momentum. So this one is like so this momentum like I mean like this adaptive learning is like a very broad category of work, different algorithm. But this one focuses on this specific this NAG or network of accelerated gradient.
Okay,
So this
okay.
is used in centralized learning, but can also be
I
applied
see,
in the
I see.
federated learning. This
I
scenario.
see.
So basically, this always. I think like the one thing is like we analyze it, and there's like a convergence bound analysis. But for
Yeah.
adaptive learning, so we are not clear like if there is this convergent bound, right?
There is the convergent bound, because when you consider for the large T number of training route, the rate per route is 1/T.
Oh yeah.
Yeah, that's the bound of that. But that's why I'm not too sure whether this approach, whether we can optimize that bound or
Yeah, because like one he is like I think the usually the best one, right? Like I don't think like anyone can be better than 1/T.
Yeah.
But even that everyone is 1/T, but there's still some difference, right? The factor or like the factor before it and the C, like we have this one's C1/T plus C2. So C1T and C2, so these two values can change. And if we can say show that it's C1 and C2, they are better, and still they are, it's better, right? Yeah.
Okay. Yeah.
So any questions from online? So if you have any question, you can either type on the chat or turn on your microphone. So, okay. Okay, it looks like it's all good at the moment. So if there's no further questions, so let's thanks Wei again for the talk. Okay.
Thank you very much.
So if you have any question, we can also discuss offline. Okay.
Okay, thank you very much. So if you are interested in like for this collaboration, and we can also have this discussion offline. Yeah, thank you very much.